Hi everyone, this is Dr. Saida Fallafini from Cal Poly Pomona. In this video, I want to talk about stochastic processes and more specifically Markov chain. Sometimes we are interested in analyzing some characteristics of interest in systems where those characteristics of interest are changing randomly over time. For example, if consider a manufacturing facility, we are interested to monitor the profit and the revenue and the cost of this facility. And these characteristics of interest are not fixed over time. They are changing randomly over time. And we are interested in predicting the value of these characteristics of interest. If we consider weather condition as another example, some of the characteristics of interest that we want to monitor are temperature or level of precipitation. We want to be able to monitor these characteristics of interest over time. They are not fixed, they are going to change randomly over time, and we want to be able to predict the values of these characteristics of interest in future. Another very good example is the stock market. In the stock market, the characteristics of interest obviously are the value of the stocks. These values are not fixed, they are changing randomly over time, and we are interested in predicting the value of these stocks in future so that we can make decision based on those predictions. We can decide if we want to sell some of the stocks that we have or if we want to buy some new stocks. Okay. So all these examples are related to the systems that have some characteristics of interest. These characteristics of interest are not fixed. They are changing randomly over time, and we are interested in monitoring those characteristics of interest and predicting the value of those characteristics in the future. Stochastic processes concept is helping us to analyze those type of systems. Okay, let's look at some notations and definitions related to stochastic processes. First of all, all the characteristics of interest that we want to monitor over time form what we call as the state of the system. Okay, so the state of the system is the set of all those characteristics of interest that we are monitoring over time. Okay, so we have a notation for those characteristics of interest or the state of the system. We usually use random variable x to show those characteristics of interest. For example, when I say xt, it means the value of that characteristic or those characteristics of interest at time t. For example, if profit is the characteristic of interest that I'm looking at, that would be profit at time t. If we have more than one characteristic of interest, then x would be a vector of those characteristics. For example, x that at time t can be profit and cost, for example. If these are the two characteristics of interest, then my xt will be a vector of those characteristics, and I want to know the value of these characteristics at time t. Okay, so now if we are interested in monitoring and recording the value of these characteristics of interest at discrete points of time, we call that system a discrete time stochastic process. Okay, so what does that mean? For example, for the stock market, let's assume we are interested in monitoring and recording the value of the stock as the characteristic of interest at the end of each day. So at the end of each day, we record what is the stock value. In that scenario, we record this characteristic of interest, or we monitor the characteristic of interest at discrete points of time, and those discrete points are basically the end of each working day. Okay, so those systems are called discrete time stochastic processes. However, we also have systems that are called continuous time stochastic processes. In those systems, the characteristic of interest should be monitored continuously over time. For example, if I look at the level of the water in a dam or in a reservoir, the level of the water is changing continuously over time, and based on the level of precipitation or evaporation that we get, and we may be interested in looking at the level of the water and how it is changing at continuous points of time. In that scenario, we call that system a continuous time stochastic process, meaning that in that system the state variable or those characteristics of interest are changing continuously over time, and we are interested in monitoring their change in continuously over time. The systems that we are going to study in this chapter are in the category of discrete time stochastic processes. So that's why the state of the system is changing at discrete points of time. At time 0, for example, at time 1, at time 2, and so those are all discrete points of time. Okay, now let's see what is a Markov chain. I'm going to explain it here. Let's assume we know the value of the state of the system at time 0 at the very start, and the value of the characteristic of interest is I0. I'm just going to show it with I0. I know also this characteristic of interest at time 1, and the value has been recorded as I1. I also know the characteristic of interest at time 2, and the value has been recorded as I2. And I know all the values all the way to x t minus 1 and all the way to xt. Okay, so I look at the value of the characteristic of interest at discrete points of time, and I have recorded the value of those characteristic of interest. So remember what I told you, what we want to do is that look at the history of the system in the past and predict what is going to happen in the future. Okay, so this is basically what is happening. So we want to look at the history of the system in the past all the way till time t and predict what is going to happen in the next time step, time t plus 1. Okay, so if in a stochastic system this prediction of what is going to happen in the next time step does not need the whole history of the past, and all I need is what has happened in the previous time step, we call that stochastic process a Markov chain. Markov chains are systems in which prediction of the future needs only where we are right now. Okay, if I know where am I right now at time t, I can predict where am I going to be at time t plus 1 in the next time step. I don't need the whole history of the past. I just need to know where I am right now. Okay, so those type of stochastic systems are Markov chains. And again, Markov chains are the type of systems or stochastic systems that we are going to analyze in this chapter. What is a transition in a stochastic system? So let me give you one more definition before I tell you what is the transition. Okay, we said we are going to use random variable x to show the value of the characteristic of interest or characteristics of interest of a system at any time t. Okay, so this is what I also call as state of the system. Okay, so state of the system is one characteristic or a set of characteristics of interest that I want to monitor. We usually don't know what is going to be the value of this characteristic of interest or what is going to be the value of the state of the system, but we have a sense of the possible values of these characteristics of interest in the future. For example, if I'm looking at a weather system and weather condition is the characteristic of interest that I want to monitor, at the very general, I can say that weather condition is either sunny or cloudy. Okay, I don't know exactly what is going to happen tomorrow, if it's going to be sunny or cloudy, but I know that it's going to be one of them. Okay, so that means the state of the system, which is represented by the weather condition, is going to be either sunny or cloudy. So I know the two possible values that I'm going to get, but I don't know exactly which one of them will happen. So when I have the set of all possible values, this is what I call as state space. Okay, another example in the stock market, for example, the stock price is the characteristic of interest. So that's the one that basically shows the state of the system. I don't know exactly what is going to be the stock price tomorrow, but I have a sense of the range of possible values that the stock is going to get. So for example, for a specific stock, it may vary anywhere between $300 to all the way to $500. Okay, and so this range is what is going to be my state space for this characteristic of interest in this system. Now let's assume for this example, for the weather condition example, we know that at time t, say right now, the weather is sunny. Okay, I want to see what is the chance that tomorrow at period t plus 1, the weather is sunny as well. Okay, so those are the predictions that we are interested to do. So when the system at time t is at any state, let's say state I, and then at time t plus 1, it goes to any other state, let's say state j, we call this a transition. We say that the system has made a transition from state I to state j. Okay, so this is called a transition. When the stock value at the end of today is $400, for example, and then tomorrow at the end of the day, the stock value goes to $450, the system is making a transition from the state I, for example, to state j. So in one time step, we have gone from $400 to $450. So system has made a transition from state I, typical state I, to state j. Okay, this is what we call as transition in the stochastic processes. We are at state I in one time period, and then we move to state j in the next time period, and we call that a transition from state I to state j. I don't know exactly if right now I'm at state I, where am I going to be in the next time step or in the next period, but we know the probabilities of all possible transitions, meaning that if at time t I'm at state I know the probability that in the next period or in the next time step I end up at state j. I know all these probabilities related to all possible transitions. So this is what I call as transition probabilities. So the transition probabilities are basically the probabilities that we are at state I, let's say in the typical state I at time t, and then we want to know the probability that at time t plus 1 in the next time step, we end up at the typical state j. Okay, so these probabilities are the ones that we have to know for any stochastic system to be able to analyze those systems. And these transition probabilities are shown usually by the notation Pij. So Pij is basically what I call as transition probability from state I to state j. Okay, now if these transition probabilities do not change over time, meaning that I will tell you that at time t, at time 10, we are at a state I, and we want to know what is the probability that in the next time step 11, we end up at state j. Okay, so this transition probability is, I'm going to show it by Pij. And now let's assume I'm looking at a different time period. Let's say we are now at time period 15 and we are at a state I, and we want to know what is the probability that in the next time period, period 16, we end up at state j. Okay, this probability, again, this transition probability is going to be Pij. If that is the case in a stochastic system, which means that the probability of transition from any state I to any state j does not depend on the time that this transition happens. It can be any time, and the probability is not changing over time. What we have is a stationary Markov chain, meaning that the transition probabilities are not changing over time. It doesn't matter if I'm at period 10 and I want to make a transition, find the probability of transition in period 11, or if I'm at period 15 and I want to know what is the probability that I make a transition to state j at period 16. Okay, the transition probabilities that we have are not changing over time. So in that scenario, we have a stationary Markov chain, and the type of systems we are analyzing in this chapter are stationary Markov chains. Okay. Next, I want to introduce what is the transition probability matrix, and I'm just going to do that in this slide. I told you that we are going to use the notation xt to show the state of the system, the value of the characteristic of interest at any time t. We don't know exactly what is going to be the value of the characteristic of interest or the state of the system in the next time period, but we know the set of possible values. So that's my state space. Okay, so let's assume for a typical system, the system has s possible value. The state of the system has s possible value. So I'm going to show the first possible value by 1, second possible value by 2, all the way to I, all the way to s. Okay, that shows the state of the system can get s possible values. So I want to see what is the probability of transitions between these possible states. So I'm going to put together a matrix. Here on the rows of the matrix, I'm going to list all possible states. State 1, state 2, state 3, all the way to state I, all the way to state S. Okay. So here also in the columns of this matrix, I'm going to list all the possible states. With state 1, state 2, all the way to, let's say, state J, all the way to state S. Okay, so if I have S possible state for the system, I will have S rows and S columns. Okay, so each element of this matrix shows the probability of transition from any state I on the rows to any state J in the column. So let's say the first element here, so I'm going to show it by P11. This is the probability of transition from state 1 to state 1, meaning that if at any point of time I'm at the state 1, what is the probability that I stay in the same state in the next time period? The next element is P12, meaning that if at time t I'm at state 1, what is the probability that in the next time step I end up at the state 2? This one would be P1j. If I'm at the state 1 right now, what is the probability that in the next time step I end up at the state j? And P1s means that if I'm at state 1 right now, what is the probability that in the next time step I end up at the state s? Similarly, for the second row, P21, meaning that you are at state 2 right now, what is the probability that you end up at the state 1 in the next time step? P22, P2j, P2s. Okay, and for any typical row I, this would be Pi1, meaning that right now I'm at the state I. What is the chance that in the next time step I end up at the state 1? Pi2, Pij, meaning that right now I'm at the state I. What is the probability that in the next time step I end up at the state j? And then Pis, and similarly I have it for the last row, Ps1, Ps2, Psj, and then Pss. Okay, meaning that right now I'm at the state S at time t. What is the chance that in the next time period t plus 1 I'm still at the same state? Okay, so if I have all these transition probabilities between all these possible states in this system, this is what I call as transition probability matrix, and I show it with P, capital P. Okay, so to be able to analyze any stochastic systems and predict the behavior of those characteristics of interest, those random characteristics of interest in the future, you have to know the transition probability matrix associated with that system. I also want to talk a little more about the whole concept of Timestep that we use over and over in our conversation. As I told you, these transition probabilities are telling us that if we are at the state I right now, what is the probability that in the next time step or in the next period we end up at the state J. Okay, so time step basically is something that you define based on the characteristics, based on the problem of interest that you are analyzing. For example, if I'm looking at the stock value and I'm recording the stock value at the end of each day, then the time step in this problem is a day. Okay, so the time step for this specific problem is a day, because I record the value of the characteristic of interest, which is the stock value, at the end of each day. If, for example, I'm looking at the temperature in weather system and I'm recording the temperature every hour, then the time step in this system will be hour. For some systems, we are looking at the characteristic of interest maybe each quarter. For example, if I'm looking at the profit or revenue or cost, I may report or record these values every quarter. And in those scenarios, the time step that I'm using and that in that system is quarter. Or even sometimes we may look at some characteristic of interest for a population those we are interested in recording those values and monitoring those values over a year. So in those scenarios, the time step that I'm using in that system is a year, meaning that I'm interested to know what is the probability that the system who is at the state I this year ends up at the state J in the next year. So you decide what is the time step that makes more sense for you given the problem that you are analyzing. One more very important characteristics that we need to know about the transition probability matrices P is that the sum of the numbers of each row always equals to 1. So if I add all these probabilities, so if I add the probabilities that go from state 1 to any state J, and I add these when J varies from 1 to S, this is going to be 1. So what I wrote here basically is the sum of probabilities that are in row 1. P11 plus P12 all the way plus P1S, that sum equals to 1. So what does that mean? So if I'm at state 1 right now, in the next time step, I end up at state 1 or state 2 or state 3 all the way to state S. So the sum of these probabilities will end up 1 because I have to definitely end up at one of these states. Either I stay in the same place or I will make a transition to one of these states. So the sum of these probabilities, meaning 1, is 1 because I'll definitely end up at one of these other possible states. Okay, the same for the same for row 2, all the rows to the very end. Okay, so for any typical row I can write this as probability of going from state I, any typical row I, going to any typical state J, and I wanna add all these probabilities together. Okay, so state J is the one that is changing. So J goes from 1 to S. So I go from state I to state 1. I go from state I to state 2. I go from state I to state J. I go from state I to a state S. Okay, so the sum of all these probabilities is 1. So this condition should hold for all transition probability matrices. This is one thing that you can always double check. When you put together the transition probability matrix, you have to check this condition and make sure the sum of the probabilities that you put on each specific row adds up to 1. And that if that's not the case, then there's a mistake somewhere. I want to introduce one more concept, and that's initial probability distribution. So what is that? So everything that I talk about in the transition probability matrix are probability of transitions, meaning that if you are at state I right now, what is the probability that you end up at a typical state J? So these are transition probabilities. However, at the very start, I don't know exactly where the system is. So at the very start, at time 0, the system can be in any one of those possible states. So let's say I call it a state I. So this probability that at time 0 at the very start the system is at the state I, I'm going to show it with Qi. And if I have this probability for all those possible states, I can list them. So I can say probability that at time 0 at the very start I'm at the state 1, for example, that's Q1. Probability that at the very start I'm at state 2, I'm going to call it Q2, all the way down to probability that at the very start I'm at state S, and I'm going to call it QS. If I have the probabilities of all these probabilities, Q1, Q2, all the way to QS, that's what I call as vector Q, and that's what I mean by initial probability distribution. Okay, so vector Q basically shows the chance that we are at any one of those possible states. Remember, for a typical stochastic system, I set the setup state space, the set of all possible values that the state variable can get. I'm going to show it by 1, 2, all the way to S, meaning that in this system, the state of the system can get S possible values over time. We don't know exactly what is going to be the value in the next time step, but we know it's going to be one of these S possible values. So if we know the probabilities that I can be at any one of these specific states at the very start at time 0, and I put those probabilities together, I have what I call as initial probability distribution. So that shows that at the very start, when we want to analyze the stochastic system, where can be potentially. Sometimes for some systems, we know exactly where we are at the very start. If we know that, that's perfect. Then the probability of that specific state would be 1, and the rest of the states will get the probability of 0, meaning that we know exactly we are at this specific state. But for some states, we don't know exactly where are we initially, and we want to make some predictions about the future, and that prediction requires us to make some assumptions about where we have started from. And if we need to do that, then these initial probability distributions are going to be helpful. Later we'll go through examples and I will show you the application of these initial probability distributions, so you will get a better sense of this concept.